So this particular question is laid out very similarly to this question type that you would get in a SACE exam. The first parts would be, can you plot the points? Can you draw a line through it? But we haven't interpreted anything about this yet. So we need to get into the idea of the fact that the least squares regression line predicts things. The line of best fit or least squares regression line predicts the data points. These purple dots aren't predictions. Those purple dots are the actual data. But then my calculator looked at all that data and it came up with an equation that predicts what it thinks all the dots should be. Okay? So do we actually have any data for time 35? Can you see how there's no purple dot at time 35? Mm-hmm. But the line tells me that it should be around 41 or 42. So the point of the equation is so that we can use maths to predict data that we don't have. Okay? That line goes on forever. We could use that equation to predict what happens if I left the car in for 100 minutes, right? But predicting for 100, a little dodgy. That's what we're going into talking about now. This might be useful in bio and stuff when you talk about extrapolation and interpolation. So that line and the equation, that only comes from the data that we use to generate it. The line indicates what's mathematically predicted to be the relationship between x and y, but the line goes beyond the farthest data points on the left and right sides. If we use the line equation to make data predictions, beyond the data we have, it's got two names. It's called interpolation and extrapolation. If you use the line to predict within your data set, that's called interpolation. That's reasonable to do if your R is strong. Do you agree that if I made this blue line out of my red dots here, it should be pretty fair for me to use that line to predict this red laser point here? Because these dots are pretty close and pretty strong. So interpolation is generally okay as long as your R is over 50 or something. If it's like 0.1, no, you wouldn't do it because these dots would be all over the place anyway. The other option is if you use the line equation to predict outside your data, that's called extrapolation. So can you see in my diagram here, these are the data points that we use to make the line of best fit. Interpolation is between the smallest data point and the highest data point. It's okay for me to use the line to predict data here because I have data that exists that's going to be close to that. Do I have any data points out this way?
Nope.
Do I have any data points down this way?
Nope.
Do I know for sure that this relationship continues in a straight line up that way? I don't know. I could draw a freaking smiley face. I don't know. We don't have the data to support that. So if you're asked a question about is extrapolation okay, be very specific about it. It's only reasonable if the extrapolation is not far. So let's say it asks you to predict data point sort of here. Is that really far from our existing data?
Nope.
No, so it's sort of fair. Extrapolation out here, would that be fair?
No.
That's really far from our existing data. That's really taking a chance to say that that line's going to continue. Okay? So extrapolation is only going to be okay if it's not far from the existing data and if the correlation was very strong. So you're going to have questions in your exam that go, okay, we made this equation. Is it fair to predict out here? Yeah, only if it's close. Only if it's close and only if the relationship is really strong. Okay? So you've got that diagram to point out here. It's better that we continue the example. So using the same data from 6 cars left in the sun, what does Pearson's correlation coefficient indicate about the relationship between time duration? So go back to your data that we entered, Calc, Lin, Reg. Which one of these, which one is Pearson's? Is R squared Pearson's or is R Pearson's? Look at your notes from previous. Pearson's was the first one we did, yeah? R. Pearson's is R. So your answer to this would be, what does Pearson's correlation coefficient indicate? I lost track of my writing. R equals, according to the calculator, 0.97. Look back at your notes. What does the table say an R of 0.97 should be said to be? It's going to be strong, but is it very strong? Have a look, just quick. I don't want to up for grabs or anything. That's why you got the table. 0.97. What would R be?
Very strong.
Very strong. So, therefore, very strong, positive correlation. What does the slope of the least squares regression line mean in context? Well, if I look at the slope, A is 0.37 to 2 decimal points. So in context, that's telling me every, what's the x-axis? X-axis was in minutes. So that's telling me every 1 minute, temperature increases by 0.37 degrees. I think that's Celsius. That's how you interpret the slope. Whatever 1 unit of the x-axis is, the slope is how much it goes up by or down by if it was negative. Use the equation of the least squares regression line to estimate the temp of a car left for 20 minutes. So the equation was T. Do you remember what we wrote for the equation? If you've been getting the notes, the T was 0.37. Lots of.
Yeah, so in this case, T times 20 equals 0.37
times 20
plus 27.03.
Yeah, 27.03 was the y-intercept. I just need to work that out. Second clear. 0.37 times 20. Add 27.03. 34.43 degrees to 2 decimal points. Use the equation of the least squares regression line to estimate the time a car would need to be left to reach 60 degrees. This is different because it's telling me the temperature. My equation is the temperature equals 0.37 times by duration plus 27.03. Which of these letters do I know in question G? Is it T that I know in question G, or is it the D this time?
D.
Sorry? No, D was this one. I knew it was 20 minutes. This question is telling me the temperature was 60. So my equation this time looks like this. 60 equals 0.37 D plus 27.03. You need to think back. We got some algebra back here. I need to get D by itself. So I need to get rid of that add 27.03. What's the opposite of adding 27.03 to something?
Taking 27.
Taking it away. Take 27.03 away from both sides. This is going to disappear, but this number is going to be 60 minus 27.03. So the left-hand side is going to be 32.97 now, is 0.37 D. What's that 0.37 doing to D? There's a sign in maths that we don't write in algebra. We write add. Multiplying. What's the opposite of multiplying something by 0.37? Divide both sides by 0.37 to get D. So D is going to be 32.97 divided by 0.37, 89.11 minutes to 2 decimal points. Give you some time to get that because there's only one more question left. Comment on the reliability of the estimates in F and G. Well, F. What kind of prediction was F? Was F an extrapolation or interpolation? Was 20 minutes within the data that we used for those cars?
Yep.
Yes. Interpolation. F was interpolation, and because the correlation is very strong, this would be reliable. because it's within the data that we collected, and we already established that the strength of that correlation is really strong. I'm not going out on a limb to use my equation to say that a car left for 20 minutes is going to be 34.43 degrees. If I look at my data, I'm going to scroll up real quick. My math said 20 minutes, 34. That's pretty much bang on where the line should be. Can you see that? 20 minutes here. Go up. It says it should be around 35. So that's reliable. It's fair to do that interpolation. But then the last one, G is predicting what happens at 89.11 minutes. Do we have any data anywhere near 81 minutes? That would be freaking out here somewhere. Even though this relationship is very strong, do we have any supporting information to suggest that that line's going to continue going straight up? No. Because what happens in real life? It's going to flatten out. It's going to flatten out to the temperature outside. We don't know that. So you would say in this question, is G as reliable as F? No. Because it's a massive extrapolation. It's way far from the data that we've got. So G was an extreme extrapolation, and even though the correlation is very strong, this would not be reliable. That's how you would answer the extra interpretation ones. So what have I shown today? How you draw the line of best fit, and then how we use that line of best fit equation to answer more interpretive questions later. I know that was a long one, but that's like one of the main question types that we do in this half of statistics. Okay? Because we try this. If it's not a line, we try exponential. That's it. There's only two possible options that we do for graphing something and seeing an equation that fits it. Okay? So I'll stop the recording there.